Welcome to The Explainer. Today, we're diving deep, and I mean really deep, into the world of nanoscience. We're going to explore how scientists figured out a way to see the unseeable, the invisible forces that literally hold our world together at the atomic level. And you know what the craziest part is? It all came from a really clever idea in a 1997 physics dissertation.
So let's just start with a really basic question. How do you see a force? I mean, you can feel a push, right? You see the result of a force, like a ball soaring through the air, but you can't actually see the force itself. Now, if that's a challenge for us in our big world, just imagine trying to see the forces happening between individual atoms. How on earth do you do that? And that right there, that's the core of our story today. We're going to see how science bridged this huge gap from the forces we can feel every day, like the friction that keeps your feet on the ground, to these incredibly tiny, kind of mysterious forces that run the whole show at the nanoscale. Yeah, think about it like this. When you rub your hands together, you feel the heat from friction, you feel the resistance, but you can't see the force itself. Now, shrink that down, way, way down. Imagine trying to understand the friction between a microscopic needle and a single layer of atoms. At that scale, these invisible forces, well, they aren't just minor details. They're everything. They dictate how things work. So scientists absolutely had to find a way to see them. The key that unlocked this new world was a device called the Scanning Probe Microscope, or SPM. Its invention was a total game changer, giving us, for the first time, this incredible window into the atomic landscape. So these microscopes are amazing. They basically work by dragging this ultrafine tip across a surface, kind of like a needle on a record player, and they build these stunningly detailed maps, atom by atom. You can see all the little bumps and valleys. But that amazing ability brought up a whole new question. As that tip is moving across the surface, what about the tiny, sideways, frictional forces tugging on it? How in the world could you measure, let alone map, those forces? And this, right here, is where the big breakthrough happens. The solution came from Dr. Chang Shen in his 1997 dissertation, and it was just so elegant. He realized he didn't need a new machine. He could use the microscope's own images to pull back the curtain and see these hidden forces.
The method he came up with is actually pretty straightforward when you break it down. First, you take a super high-resolution picture of a surface. Then, you take another picture of the exact same spot. After that, a computer gets to work, playing what's basically an atomic scale game of spot the difference. It looks at tiny little patches from both images and calculates if there was any microscopic sideways shift between them. By doing that for the entire surface, it creates something completely new. A map, not of the surface itself, but of the invisible forces acting on it.
And this technique has a name: lateral displacement mapping. It's all about turning two regular 2D images into this incredibly rich map of hidden forces. And here's the key takeaway, the real secret sauce. The important information wasn't in any one image. It was hidden in the tiny, almost imperceptible differences between two of them.
Okay, so Dr. Shen and his team have this powerful new tool. What do? They test it on something with a really predictable surface, a hologram. Holograms have these very regular, repeating, wavy patterns. So the team had a pretty clear idea of what they thought they would see. But, science rarely goes exactly as planned. The logic here was totally sound. A hologram surface is basically a perfect wave. It goes up, then down, then up, then down. So they figured, okay, the map of the friction force should look exactly the same. For every peak on the surface, there should be one peak of friction. Made total sense, but that is not what they saw. Not at all. Instead of one peak of friction for every wave on the surface, get this. The map showed two peaks. For every single up and down of the surface wave, the force map had this double peak pattern. The frequency of the pattern, as scientists call it, had literally doubled. What was going on? Well, that doubled pattern was actually a huge clue. It was a telltale sign that the friction they were measuring wasn't just about how high or low the surface was. No, it was all about the slope. Think about it. Any wave has two slopes, right? There's the uphill part and the downhill part, and the force was strongest on those slopes. This was a beautiful experimental confirmation of a core idea in physics, that the force of friction is proportional to the normal force, the force pushing the two surfaces together. So this surprising result wasn't just a curiosity, it was definitive proof that the method worked. But the real genius here wasn't just in what it could do, but how it did it. This wasn't some new billion-dollar piece of equipment. This entire breakthrough was powered by a simple, really clever idea.
And this right here, this is maybe the most powerful line in the entire paper. I'm quoting directly from the abstract.
The method is applicable to all scanning tip microscopes without additional special hardware. Just think about that for a second. With some clever software, any lab, anywhere in the world, with a standard microscope could suddenly do this incredibly advanced analysis. It was like a free, massive upgrade for the entire field of nanoscience.
And the potential applications just exploded from there. This wasn't just about friction anymore. You could use the same core idea to turn a pair of 2D images into a 3D map. You could use it to watch how a surface physically changes over time, or even to analyze all the different forces acting on the microscope tip itself. The concept was so flexible it could even be used outside of microscopy altogether.
And you can see that this elegant idea was backed up by some serious scientific heavy lifting. Just look at the dissertation chapters. It lays out the whole journey, from reviewing all the existing science to developing the method, and even creating a complete theory to explain that surprising doubled frequency they discovered.
So in the end, by just looking at two flat images in a new way, an entire map of invisible forces was revealed. It really makes you wonder, doesn't it? What other huge discoveries are just sitting there, hidden in plain sight, waiting for someone to just look at the data a little differently? What other invisible worlds are we completely missing?